So now that we've learned how to find the derivative of a natural log function, let's work in reverse and integrate a natural log function. So we only have two objectives here. One is to use the log rule for integration to integrate a rational function and then to integrate trigonometric functions. So in our last section, we just learned all of the differentiation rules for logarithms. They were pretty straightforward. And we know that differentiation and integration are opposites of one another, they're inverses. So it would make sense that if I'm going in reverse and I'm integrating 1 over x, then I'm going to get the natural log of the absolute value of x. And keep in mind, the reason that we have to use that absolute value, like we finished off with in our last video, is because that always makes that positive, and I can only take the natural log of a positive value. And then don't forget, if it's an indefinite integral, we always use plus c. Same thing is going to be true if I end up with a function that has a chain rule component to it. So if I've got a u, it's going to be important for me. I'm going to probably go back to that change of variables U-substitution, where I need to make sure that I have u prime also in here. So remember when we said du had to be the derivative of u, that's what we're going to have to do again. So notice here we're going to do some straightforward examples, which means we're just going to be using that definition that we just came up with. So for the first one here, the first thing I would do is say, well, this is actually 2 times 1 over x dx. So you can take the 2 out of it. You don't need to worry about it. So if you take the 2 out of it, then we know the integral of 1 over x dx is the natural log of the absolute value of x, because that's the definition. That's why I called this a straightforward example. I didn't have to do anything crazy. So then I'm just taking 2 times that because I had the 2. Don't forget the plus c. Same thing is going to be true for the second one. I'm going to take the 5 and pop it to the outside. So the 5 on the outside, and then integral of 1 over x minus 1 gives me the natural log function of the absolute value of x minus 1 plus c. So let's look at a more difficult example, and this goes back to when we learned pattern recognition or change of variables. So this was at the end of chapter 4, so if you need to go back and review those videos, it's the same idea. I showed you 2 different methods, so I'm going to show this first one using both of those methods. But what I want you to understand is when I'm integrating something like this, I really need this to be the integration of u prime over u. So if I have something like this, which has a derivative, then I need to make sure that that derivative is included. So using the first method, which is the way that I've shown you here, which is pattern recognition, that's what I'm going to be thinking about is u prime over u. And then I'll show you the second way, which was change of variables, which works equally as well. So it's whichever method you like better. So here, if I have u prime over u, then I know if u is 4x minus 1, and of course I'm going to let u be the denominator because that's what I want, is 1 over u, right? So u is 4x minus 1. du would be 4 dx, so 4 because that's the derivative. So what I have to do is I have to multiply by 4 on the inside so that it's in the u prime over u position. And then on the outside, because I've multiplied by 4 and I can't just randomly multiply by 4, I have to multiply by 1/4 so that it works out to me really just multiplying by 1. So that's what I've done here. I've used, obviously, pattern recognition using u prime over u. From here, it's pretty straightforward. I've got 1/4 on the outside. The integral of 1 over u du is natural log of the absolute value of u. And then I just take u and plug it back in. Now, if you liked the other way, which was change of variables, I would still let u be 4x minus 1. Then I would say, well, du over dx is equal to 4, which means dx is equal to du divided by 4. So that's the other way to think about this. So this would be then the integral of 1 over u times dx, because that's what let me get rid of the 4's here. 1 over u and then dx I've replaced with du over 4. And then I said, well, I don't like that 4 on the inside, and so I'm going to rewrite that as 1/4 integral of 1 over u du. And so notice here it's exactly the same, and I would finish it the exact same way. So again, I don't care if you use change of variables or if you use pattern recognition. You probably have your own method that you like better that works for you. That's the one you should go with. So here's one for you to try, and again, make sure you know all of the derivatives of trig functions, etc. Not a bad idea to have that little handout by your side so that you don't have to keep flipping back through your notebook. But notice I've already sort of given it away for you here before I even started working it out. Of course we're going to let u equal tangent of x because we always want u to be whatever's in our denominator. It just so happens that the derivative of tangent is secant squared x, and that's what we have. And so as you can see, we already have basically u prime over u, or 1 over u du. Remember, this is the exact same thing as this. So if we write it this way, that's okay. Either way, we're deriving with respect to u. So that means my integral of that is natural log of the absolute value of u plus c, and then we just plug u back in. So natural log of tangent x plus c. Let's take this now to the next level, and so now this is a definite integral. So here we're actually finding the area, so we're not just doing this symbolically with the plus c. We now have limits of integration. And the upper limit of integration is the line x equals 3, and they don't specify a lower limit of integration, but because, again, we're dealing with this function that we know the domain is positive values, so we know that we're going to use x equals 0 as my lower limit of integration. And then, of course, here's the function that's also going to define the area that we're going to find. What I can do then is two different ways, and I've only shown you one of the ways. I'm hopeful that you'll remember the other way from previous lessons. If I say that u is x squared plus 1, when the derivative of u would therefore be 2x dx, then I can certainly take this, and it looks like I forgot my dx, but you get the idea. I can take this and rewrite it, because I know that I need 2x dx, so I've replaced the 1/2 here and the 2 here, because again, that's essentially multiplying by 1. And if you'll notice, I never actually substituted u. So I used the u here to help me determine if I needed to multiply by something like 2 and 1/2. But I didn't actually substitute it in, and let me explain why I did that. Because now, when I take the integral, which of course is going to give me the natural log of the absolute value of x squared plus 1 with the 1/2 on the outside, notice my limits of integration are still 0 and 3. So if I had, let me just remind you real quick, if I had actually plugged it in and said this is 1/2 integral of u prime over u, then I would integrate from, I would have to say, let's put in 0 squared plus 1, and then what's the other? 3 squared plus 1. So I would then be going from 1 to 10. So if I would have kept it in the u's, I'd be going from 1 to 10. So this would then be 1/2 and then natural log of u from 1 to 10. And it's really going to give me the same thing, because if I took the natural log of 10 minus the natural log of 1, as you can see, that's exactly what I ended up with here. So really it doesn't matter to me if you keep the limits of integration at 0, 3, keeping the x squared value in there, or if I switch everything over to u's like I have here, then I have to change my limits of integration in order for everything to work out. But as you can see, everything is still going to turn out to be the same value, but I will be checking for that. So if you kept everything over here in the U-substitution, you need to change these values accordingly, otherwise you'll get the wrong answer. And if you go ahead and plug the x value, whatever u is equal to, back in, then you don't have to change your limits of integration. So here's one for you to try on your own. We are trying to find the area of the region bound by the graph of y equals x squared plus 1/3 divided by x cubed plus x. And then of course the limits of integration would go from 1 to 3. So press pause, try this question, then press play to see how you did. So first thing I would do is of course define u, and I'm going to always define u as my denominator, so x cubed plus x. And then from here, that should be a cubed. I said cubed, I just didn't write it. And then from here you get to kind of choose. If you just say, well, du would be, or u prime, it really doesn't matter because they're kind of the same thing. So u prime is 3x squared plus 1, so I can think of it that way. Or remember, we could say du over dx equals 3x squared plus 1. That means dx is equal to du divided by 3x plus 1. It really doesn't matter to me which way you do it. I prefer this first way, so that's the way that I'm going to continue, but both ways work just fine. What I find out here is when I'm dealing with this, I actually have to multiply by 3 to make this 3x squared plus 1, which means on the outside I had to put the 1/3. So again, now it's pretty straightforward. 1/3 natural log of u. And then I know that I'm going to plug back in my value for u, because notice on this one, again, I didn't change the limits of integration. I could have changed the limits of integration and kept it as 1/3 natural log of u from, let's see, 1 would be from 2, and if I plugged in 3, I would get 27 plus 3, which is 30. And I would get the same thing each way, and again, down here you can see that I would get the same thing, natural log of 30, natural log of 2. It's going to be the same thing whether I keep it in u or plug the x's back in and use the original limits of integration. So just make sure you're clear when you're showing work which way you did it. But then from here the work is pretty similar, and either way I end up with 0.9026834, etc., etc. So this one's not super fun, and the reason for that is if I started doing what I normally do, which is to say u is x squared plus 1, then du would be 2x. And I don't have that. Up here, if you'll notice, I've got an x squared on top as well, and if I take the derivative of x squared, I'm never going to get x squared. So I can't use pattern recognition or U-substitution because it doesn't fit. So I'm going to start by using long division. So this is obviously a last resort when other things don't work, because it's not super fun. So what I'm going to do is I'm going to take my numerator, obviously divided by my denominator, and if you'll remember, what we're looking for when we're doing long division is looking at that first term and saying, what would I take times this guy to get this guy? And that would just be 1. Then what we do is we take 1 times all of this and place it beneath the first one. So 1 times x squared is x squared, 1 times 1 is 1, and then I'm going to subtract those. So x squared minus x squared goes away. This should be x minus 0, so that's where the x came from, and then 1 minus 1 goes away. And so x is actually considered a remainder. And whenever we have a remainder, we always write it over whatever the original denominator is. So that's where this solution came from, is the 1, because it went in one time perfectly with a remainder of x divided by x squared plus 1. So what that does for me now is I can continue to integrate this now that I've simplified it a little bit. So now that I have this guy rewritten using long division, now I'm going to find the derivative of each one. So essentially I'm finding the derivative of 1, I'm sorry, the antiderivative of 1, and then the antiderivative of this guy. And again, here is where I'm going to use my U-substitution. So u is x squared plus 1, du is 2x dx, and so that means I'm going to have to take this guy times 2 to make that fit the pattern, and that's where the 1/2 and the 2 came from. And then from here, it's pretty straightforward. Obviously, the integral of 1 is x. The integral, keep the 1/2 on the outside, of all of this is u prime over u, and so that's just natural log of u, which is all of this, plus c. I know this video is getting a little lengthy, but I wanted to make sure I gave you plenty of practice. So here is a good practice of another one where obviously using that U substitution isn't going to work right away. So go ahead and try this question, then press play to see how you did. So again, I had to do long division here as well, because if I started out with u as x squared plus 3, then du would just be 2x, and that doesn't work because I've got an x cubed on the top. So that's when I know that I'm going to have to break out that long division. So that's what I did. Over here, I took x squared plus 3 into my numerator, and this one was a little lengthier, but again, the first step was look at the x squared and the x cubed and say, what do I take times x squared to get x cubed? I take it times x. I took x times both terms, giving me this line. And then I'm going to subtract them. So I'm subtracting the whole quantity. So x cubed minus x cubed goes away. Negative 3x squared minus 0 is negative 3x squared. 4 minus 3x is 1x. Bring down the minus 9 because it's essentially minus 0 again. Then the process repeats. So now I'm looking at x squared and negative 3x squared and saying, what is it that I have to take times x squared to get negative 3x squared? I have to take it times negative 3, so that's where minus 3 came in. So took negative 3 times this, that went down here. I'm subtracting the whole thing. So again, I'm subtracting a negative, so here I'm really just adding, and those go away. X minus nothing is x. Negative 9 minus negative 9 is really plus 9, so those go away. So again, now I have something where my remainder is x. Take the remainder over whatever the divisor was. And from here, I can integrate. So again, from here, I'm not going to go through all of the steps just because this video is already really long, but you get the idea. From here, I'm going to integrate really each part separately, and this is the part where I would use that U substitution, where u is x squared plus 3, and then du is 2x, and that's where that 1/2 is going to come into play. So I'll leave it at that, and we'll go on to the next question. This slide I threw in here just to make sure that we both remembered that there's two methods that I can use for integration, which is of course U substitution or change of variables, and I kind of showed you both of those as we went through the first couple of questions, so I'm not going to spend a lot of time on this slide. Just keep in mind your choice, which one works best for you. So here's an example where we're actually going to work through it with a change of variables, and they're so similar to one another. This guy would still be u, so u would still be x plus 1. Du would actually be just 1, but then remember we said du over dx is 1, and so then we called dx to be du divided by 1. And that's kind of what I've done here then, is I've replaced this guy with u squared. I've replaced this guy with 1, or du. So notice I didn't have to put anything on the outside here. And then this guy was 2, and then u minus 1. So this one I probably wouldn't honestly have used U substitution on or anything. But this guy turned into u minus 1 because remember x was x plus 1, and so I had to take 1 away from it for it to be 2x. I take the 2, stick it on the outside, and now I've got two separate things to integrate. So this guy is a lot easier because u to the negative 2, I don't have to use any crazy log rules. I just use my general power rule that says increase this by 1 to make it negative 1, and then divide it by that. So that's this guy. This guy fits my natural log pattern, and so I get everything in terms of u and then plug the u values back in.